Hello, everyone. Today I'm going to be talking about something which I actually find quite fascinating. I think probably a lot of people will find it less fascinating than I do. But to me, this is something really interesting. I've actually wanted to make a video about this for a long time because this is a subject that I find quite interesting, and there's not a lot of information about it online. There's surprisingly little information about making trainers for PC DOS games on the internet. Now, what's a trainer? Probably most of you know, but so most of you are familiar with the concept of cheats in games, I'm sure. A lot of games came with cheat codes built in. You could type in some secret code or do some secret thing in the game to unlock some ability, like typically getting invulnerability so you couldn't take any damage, couldn't get hurt, or unlimited ammunition or stuff like that. Typical cheats in games, right? But a trainer is a program that runs alongside the game. So it's a separate program that you run typically before the game. So first you run the trainer and then the game. And what the trainer does is it actually modifies the game's values in memory. So the trainer is literally going to go into the program memory of the running game program, and it will change values in the game to do things. Why would you want to do that? Well, a lot of games don't have cheats built in. I mean, it's convenient if a game comes with cheats built in. A lot of them do, but many of them don't. And so if the game doesn't have its own cheats, then you need to figure out other ways to cheat. A lot of you might be familiar with a program called Cheat Engine, which is very popular for Windows. It's kind of similar to what we're going to look at today, except Cheat Engine is, it's a newer thing. Like I said, it's for Windows. And back in the days of DOS, we didn't have Cheat Engine. We didn't really have stuff like, I mean, people who played games on like the NES or Sega Genesis or Mega Drive, as it was called in some markets, they might be familiar with the game Genie, which is kind of a similar idea. The game Genie basically gives you the ability to change game parameters, like to actually change game memory locations in game, and thereby giving you, again, usually things like unlimited lives, unlimited ammunition, or other nice, things, useful things, or cool things that might be nice to have in the game. So, in the context of DOS, a trainer is usually just a TSR. I made a video a couple of years ago about how to make TSRs in DOS, and I'll put a link in this video's description to my previous video on making TSRs, because most of what a trainer is really just a TSR. Like the bulk of the code that we're going to write today is just my previous TSR code. And what is a TSR? In case you don't know, the TSR stands for terminate and stay resident. Basically, that means that the program seems to finish running, but it hasn't really ended. It's still resident in memory, so it's still kind of running in the background in the computer's background memory. Early DOS PCs, like DOS didn't really have a very good concept of multitasking, but it was still possible to have multiple things running at once. So it's not like there was really only one program running at once. There were multiple things going on at once. You just didn't see them. It wasn't like Windows or other sort of contemporary graphical interfaces where you actually see several windows open at once. Even in DOS, there were multiple programs running. You just didn't see them on the screen at once, usually. So we're going to make a trainer, and it's going to be basically a TSR. So before I begin, what are the two main problems that you might have making a trainer? Like the hardest thing, usually the single biggest problem, the single hardest thing about making a trainer is just finding the memory addresses, because games don't tell you what memory address they use for certain things. So, you don't really have a good way of knowing that memory byte number 2784, for example, is where your hit points are stored, and that's the byte that you need to change to give yourself more hit points, for example. So you need to find locations in memory. That can be really difficult sometimes. And again, coming back to Cheat Engine, if you're familiar with using Cheat Engine to cheat in Windows games and stuff like that, you probably know about typical tricks using that, which involve things like searching for values that have changed. So like if you know that right now your health point, let's say right now your health is at 80 health points, then what you might do is tell Cheat Engine, look for all memory bytes in the whole game memory that have a value of 80. and then once you've told it to search for all those locations, then get hurt in the game. Like go do something in the game that takes off some hit points. So now maybe you have 70 hit points instead of 80. Now you tell Cheat Engine, look for all locations that have a value of 70 in memory instead of 80. All the locations that had 80 before, look for the ones that have 70 now. And typically you'll get several of them. You might have dozens or even hundreds or even thousands of them. But you kind of go through that process. You go through this process of narrowing down memory locations, saying, okay, it can't be this location because this location is no longer the same as the number of hit points that I have. And you kind of narrow down memory locations until you narrow it down to typically just a few. If you're lucky, just to one possibility, but if you have a few possibilities, if it's like 10 possibilities still left, then you can just manually try them, just try each of them in order until one of them works. So that's a typical thing that people do with cheat engines. You can kind of do something similar with DOS games, but it doesn't always work. And that's kind of an art in itself. So I'm not going to show the whole art and science of finding memory locations for games today. That's kind of like, that's a whole subject unto itself. But I'm going to show a relatively simple example of how you can find a memory location of a game that uses fairly simple storage for its values. The other problem that you sometimes have, and which I don't really have a solution for, and I'm actually going to put out an open call for people to tell me how to deal with this, if there is a good way to deal with this, is games that kind of take control of interrupts. So what is an interrupt? Let me go ahead and get into DOSBox. And this is not just any regular DOSBox. This is DOSBox X. It has a lot of nice features which regular DOSBox does not have. I've harped in the past about save states and how important save states are in DOSBox Down, which I've many times talked about. Well, DOSBox X has save states. Here under the capture menu, you can do save and load, so you can select different save slots to save stuff into. But it also has a debugger, which is really cool. I don't know of any other port of DOSBox that has a built-in debugger. So we're going to make extensive use of that. We're going to see that in a little bit. And it also has some nice tools on the Z drive or Z drive. It comes with stuff like... what does it come with? It comes with its own edit.com. It actually has edit.com, which is not its own thing. This is actually the FreeDOS editor. It's actually the edit from the FreeDOS operating system. But this comes with DOSBox X, which is really cool. Like that's something that regular DOSBox does not do. I don't think DOSBox has its own full screen text editor. Technically, this doesn't either. I mean, it's just copied it from FreeDOS, but the point is it comes with DOSBox X. You don't have to do anything extra to have it. It comes with DOSBox X, which is very cool. Anyway, so what I'm going to do, just as a start, is I'm going to go to Help PC, which I've used many times in the past in previous videos, and we're going to look at interrupts. So interrupts are basically built-in subroutines. They're subroutines that are built into the computer. Some of them are built into the ROM on the computer, like they're physically built into the hardware firmware code on the computer. And some of them come from DOS, from your operating system. So if you're using your PC without DOS, like if you're booting without an operating system, as you sometimes do, or as some people might, then you won't have the ones that come from DOS. For example, the very common interrupt 21, I believe, comes from DOS. So if you're not booting DOS, you won't have interrupt 21. But interrupt 10, which provides video services for things like changing video modes, for example, that is built into the video BIOS. So you'll have that in any case. You don't need any software for that. It's built into the firmware code on your computer's video card. So what we typically do, I mean, there are a couple of ways of approaching this, but a typical thing to do when you are writing a TSR is to use interrupt 8. Oh, I don't know why this happens. It's kind of odd. Help PC does this sometimes, where it needs to run build.bat, and it will then rebuild the indexes or indices for its files. I don't know why that happens. Kind of weird. Anyway, okay, let's try this again. So I wanted to look at interrupt 8. Yeah, so this is the so-called system timer interrupt, and you can see it's generated 18.2 times per second. So a typical thing to do is, if you're writing a TSR, is you basically grab this interrupt. You basically take this interrupt and use it for yourself, because the PC will try to run this interrupt 18.2 times per second. And so whatever you want to do will get done several times a second. I mean, 18.2 times a second is good enough for most of our purposes. So we're going to hook into interrupt 8. And I guess we can just get started with that. But before I do that, let me go ahead and show you an example, because again, I'm not going to talk that much about the TSR aspect itself. That's something I covered in a previous video, so I'm not going to get very much into detail on that. So just to kind of give you an idea of what we're shooting for, let's go ahead and actually do something a little bit. Let's have a little fun here and run a game. So there's a game here called Pac-Mania, which, as you might guess, is a Pac-Man clone, and it's a pretty good one. So let's go ahead and run it. This is version 1.1, programmed by Greg Seelhoff from East Lansing, Michigan. And yeah, it is quality software. I actually have to say they did a pretty good job with this. It's a pretty good port of Pac-Man. I mean, it's just a Pac-Man clone, but it's pretty well done. So let's go ahead and start the game. And you can see you run the debugger by doing left alt and pause. So let's do that. I've pressed left alt and pause, and this window has popped up. So this is the DOSBox X debugger, which again is very, very, very useful for this kind of work. I have not seen any other port of DOSBox that has this. The core DOSBox doesn't have this. DOSBox Down doesn't have this. I'd be curious to know what other DOSBox variants have this, because this is very, very useful for this kind of work. So I don't exactly know what people did back in the day. I mean, there was a time, obviously, you know, back in the days when people were actually using DOS. That was a time when you didn't have stuff like this. You weren't running DOS programs in an emulator. You were actually running them directly in DOS. So you didn't usually have a debugger like this to just start poking through the memory, you know, because you didn't have like a hypervisor or whatever, or, you know, like an emulator that was actually simulating the whole environment. So I don't know exactly what people did back in the day. At the very beginning of computing, like at the very, very, you know, early days of home computing, if some of you remember like the Altair 8080, which is sometimes considered the first home computer, it had no monitor, like it had no screen. It didn't come with a keyboard or a monitor. Its only input was a whole bunch of flip switches, and its only output was a whole bunch of LED lights, and that was it. You didn't have a screen, you didn't have a keyboard. That was your only way of getting data in and out of the machine. And it sounds very clunky, and it was in a way, but the nice thing about it was that you could directly look at any memory address. You could say, I want to see what's in memory byte 12, for example, and you would just flip the switches to form the number 12 and then say examine to look at that memory address, and it would show you exactly what was at that memory address. And there was no way for software to block this because it was built into the hardware. Like the switches and all, they were physically connected to the hardware memory controller. So at any point in time, you could always see exactly what was in memory. Today, computers don't have stuff like that. I mean, there's no computer sold today, as far as I know, that has a bunch of switches like that in the front, so you can't just physically say, I want to look at memory byte 27 or 400 or whatever. You know, it's not possible. You have to do all that through software like this, which is not necessarily bad, but it can be blocked potentially by some programs, and we'll see that a little bit later, how software might actually block your attempts to do stuff with it. So anyway, so what we're seeing here, so up here we see the CPU registers, so these are the different CPU registers and what values are in them. This is the data view, so this is what's actually in the computer's memory, and this is the code view, which is pretty much the same thing as the data view, except it's disassembly. It's showing you the assembly language instructions that the bytes in memory correspond to. So, so you can see the code segment is 820, so the program is, this game is actually running in memory segment 820, but the data sector is F61. So the data that the game is probably using is probably located in F61. So what you can do, what this debugger allows you to do, is you can change the locations of the data view or the code view with the commands D and C respectively. So if I want to say, for example, okay, I know that this game is, so it starts off with the data view at literally at 0, like this is memory byte 0, it's the very first byte in the computer's memory. But since I know that the data segment that the game is using is F61, we probably want to start looking at the data there. So I can say D for data. This is now controlling where the data view is going to point. So I can say D F61 for the segment, and I'll just say 0. And see, now it's updated. It's actually put us here. So this is the start of the game's data. Okay, and it looks like the game was written in Turbo C. That might be useful to know. Actually, probably won't be for now, but it could be useful for some other applications. And so you can see down here, it's actually showing you the disassembled code of the game. We're not going to use that today. This is definitely useful for analyzing code, but we're not working with code today. We're working with data. So what I'm going to do actually, we can do here is press Tab to switch between these 4 different sections. I'm pressing Tab to switch between the registers, the data view, code view, and output. So I'm going to tab to the data view, and now I can use the arrow keys and page up and page down to look through the data that this game is using. This is what the game is currently accessing in memory. So it looks like, okay, looks like this is a phone number for some BBS. I think these might be the high scores, actually. I think these are the high scores in the game, so that's kind of cool. So if you don't know exactly what you're looking for, it's kind of like looking for a needle in the haystack. Again, I talked about the tricks that people sometimes use with Cheat Engine, saying look for a byte that's starts off being 80, now look for a byte that became 70, now look for one of those bytes that became 60, and out of those bytes that are still left, look for one that became 50 now. You know, just keep changing values in the game and see how the memory values react until you find a memory byte that consistently responds to circumstances in the game. I'm not aware of a way to do that here. I'm not aware of a way to do that with a DOS program, and if anybody knows how to do that, please let me know, because that would make this kind of work a lot easier. But what I did, what you can do, it's a little bit more awkward, I suppose. But what you can do is, there is a command here. Actually, if you type help here, it'll give you a list of some commands that you can use in this debugger. So there's stuff like, BP, you can set breakpoints and things like that. There you see C and D to set the code and data locations, where it's showing you the code and data view. Stuff like this, I don't think we need right now. Yeah, memdump, that's the command I'm looking for. So this memdump command, it dumps a bunch of memory. You can create a memory dump with it. So let's make a big memory dump. I like big dumps, and I cannot lie. Okay, so what's the syntax? I think it was memdump, and then just the location. So let's start with, let's just start with the beginning of the data segment here. So F61 is the data segment. I'll just start from address 0. Get the whole, hopefully the whole data area that the game is using. And now we just need to type in how many bytes we want to dump. So, I don't know, let's say 100,000. I mean, how big is the game? I think the game is less than, how big is this game? Hold on, let me see. How big is this game in bytes? I mean, the executable file for this game is a little over 53,000 bytes. So, and that's it. And it has like a data file, which is less than 400 bytes. So the whole amount of data that we're working here should be less than 100,000 bytes. So I'll just say dump 100,000 bytes. That actually might be a bit excessive, but you know, that's okay. It's no harm. I mean, we can delete this file when we're done with it. So I'll go ahead and dump 100,000 bytes from memory, and it should say memory dump success. So there we go. So now we have created a dump file called, and it's just called memdump. So if you go to the folder or the directory where you installed DOSBox X, in the DOSBox X main folder, you will have a file called memdump.txt. And it looks like this. So yeah, you just see the locations and the values of the bytes that are there in memory. So this by itself is, I mean, I guess it could be useful, but it's not super useful without some context. What you really need to do, again, is kind of do something similar to what people do with Cheat Engine, where you kind of have something to compare it to. So what I'm going to go ahead and do, I'm going to close this for now, and I'm going to rename it. So I'm just going to show you my DOS prompt. Like, this is my actual Windows DOS prompt here now. So if we look at all our memdump files, okay, so we just have the one that we just made. So I'll go ahead and rename it memdump, and let's call it, let's focus on how many lives we have. So you can see we have 2 lives in Pac-Man, or Pac-Mania. So I'm going to go ahead and rename this file as memdump2, not because it's the second file of this type, but because it's going to be the dump of us having 2 lives. Okay, so that's fine. That's a good start. Now that we've done that, let's go ahead and deliberately die. I'm going to deliberately get myself killed. So back here, I'm going to close the debugger by pressing left alt pause again. There we go. We done got ourselves killed. Okay, and I'm going to again activate the debugger by pressing left alt pause, which thankfully pauses the game. Thank you, DOSBox X. So now we're looking at the code as it is now, or not the, well, the code as well, but what's more important than the code for this purpose is the data. We're not changing the code, we're just changing the data in the memory. So there are programs which also try to change the game code, like that will actually modify the game executable, but that's technically called a patch. That's patching the game's code to actually change the code itself of the game. We're not changing the game's code, we're just changing the variables, the values of the variables that it uses, in this case the variable for how many lives you have. So again, you could go looking through the data here, and that would take forever. But let's do something now. Since we have a memory dump already, let's do another one. Let's do another memdump from the same space. Let's say memory dump of address F610, and I'll do another 100,000 byte dump. Okay, dump success. So now if we come back here and look at our memdumps now. So we've got memdump2 and memdump, and I'm actually going to rename memdump. I'll rename it memdump1, again, not because it's the first file, it's actually the second file, but this is, the numbers indicate to me how many lives we have in these cases, not how many, not the sequence of the files, but how many lives we have left. So now we've got these 2 memdump files, and Windows does have an fc command, a file compare command, and what you can do is just compare memdump. Oh, it didn't rename it because I typed rem instead of ren. I meant to type ren for rename, but instead I accidentally typed rem, which it interpreted as a remark. That's right, that's why I still have, okay. Let's try this again. Okay, now I have memdump1 and memdump2, so you know, that's a situation where you need to sneeze, but it's just, excuse me. Okay, that's better. Okay, where were we? So I wanted to do an FC. I want to do a file compare on memdump1 and memdump2. And we're going to get a fair bit of output. I'm going to get a fair bit of stuff. But what I basically want to do now, if I go back to the beginning here, well, I got quite a lot of output from that. So this is basically showing all the differences between the 2 files, and you can see there are quite a lot of differences. So what you want to do is look for a byte in one of these segments here that's 1, and down here it's going to be 2, because in this section we have 2 lives, and in this section we have 1 life. So it might not be here, it might be farther down. It could be anywhere in all this text that's changed. And all these values that have changed, it could be anywhere here. Now, ideally, you'd have a much better system for doing this. Ideally, you'd have a system like Cheat Engine, again, where you could just say, look for everything that was 2, now look for everything that is 1, and then die again, and look for everything that's 0 or something like that. But I'm going to skip over. I mean, since I didn't have that facility, I just kind of manually copied the text here and just looked at everything that's, that's 2, and then looked for something that, that was a 1. So like, okay, this value is 1, and now it's 0, so that's not what we're looking for, I don't think. But stuff like that, you just kind of have to go through these bytes and see what's changed. Now, if you're asking how long does this take, I can say it didn't take me that long. I mean, it took a while, but how long is a while? I would say it took me it took less than an hour to go through this data and find the place that I was looking for. So, this is a fairly small game. I mean, it's a 50 kilobyte DOS game roughly, so it doesn't have a huge amount of data. It's doable. I mean, doing it by hand like this is possible. Obviously, it would be better to have some tools to automate that, but it is definitely doable. So let me see. I'm gonna skip over doing that, however, and jump to actually, where was it? I don't remember where it was now. Let me see if I can look up where I noted it somewhere, but I don't remember exactly where. Where did I write it down? I think it was... Let's see. I stupidly did it based on the location of the code segment instead of the data segment, which you can also do. It's just less efficient to do it that way. And I'll tell you right now, just in case you actually get it into your heads to do this, I'll tell you right now, just something to save you some time. It's actually the number of lives you have left plus 1, because the game does have a life 0, and the life 0 is signified in the memory as number 1. So even though it looks like we have 1 life here, it actually is signified in memory as 2. And if I died again, it will now be, this Pac-Man here will disappear, and the byte in memory will be 1. And when that goes down to 0, then it's game over. So actually what we want is not a byte that's 2 here and a byte that's 1 here, but a byte that's 3 here and a byte that's 2 here. I just found that out by looking. I mean, there's no real way to know that. That's just you just have to go through the bytes and find something that that jumps out at you. And you're lucky if it's that simple. I mean, this is like the simplest case where the numbers are just rendered in bare hexadecimal values in memory. So that's the simplest case. Some programmers don't like the idea of people going through their code and doing stuff like this. Some programmers don't like the idea of people using cheats or trainers or patches or cracks or whatever for their games. And so they'll make it really difficult to do stuff like this. So they won't just have the numbers in bare hexadecimal values in the memory. They'll have like some weird obfuscation going on where they're like 2 different numbers in different locations, and they're added together to form the actual value that you're looking for, or something like that. So if people are doing stuff like that, it can make it really difficult. You might really have to spend a very long time, like hours or even days, going through the code to try and figure out what's going on. So, again, this is the simplest case. It can get a lot more complicated than this. But in this case, I did find that it just took a while. Okay, let me try this then. Rather than doing this, let me get out Notepad. And what I'm going to do is I'm going to search for everything that has a value of space 03 space. Let's see. So that was 3. Okay, so that's not what we're looking for. Oh, this might be what we're looking for. Check this out. So remember I said we're looking for something that's 3 here and 2 here. So this is looking promising. So we have exactly what we're looking for here. So that could be it. This could be the value. This could be the byte that we're looking for. Let's go on just a little bit further. Do we have anything else which kind of matches that pattern? That's not going to be it because it's. Where is it? No, that's not it. That's not it. That's not it. Could be this as well. Could be this as well, because again, we have a 3 here and a 2 here. But we're already, check out where we are. We have an offset here of AA0. So this is like way past 65 like 64, 65 kilobytes past the start of the data segment. So I doubt that the game would have data this far out. It might, but it, oh, actually, no. No, sorry, I was confusing this with this. No, this is actually... Yeah, no, this wouldn't fit. Okay, I'm going to guess then. Seems like a good chance that the byte we're looking for is... Which one was it? Not that, but this one here. So it's at location 0F61 1DD 0, 1, 2, 3, 4, 5, 6, 7, 8, 9A. Okay. I'm going to write that down here just as a note. So we're looking for byte 0F61 1DDA. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9A. Yeah, because it's hexadecimal. So instead of going 9, 10, it goes 9, A, B, C, D, E, F. And then from here it starts at, rolls over to 10, becomes E0 instead of D0. Okay, so I'm guessing this is the byte we want. And we can take a look at that byte by going to, so if I say D now, so I'm changing the data part that we're looking at. So DF61 colon 1 DDA. So there's a 2 there. And I guess we can do another check if we want. We could die now and see if that 2 goes down to 1. But I'm going to take a chance and just suppose that that's probably the byte we're looking for. And I will say, what's the command? I think it's, hold on, let me look at help again. What's the command? I think it's SM for set memory. So yeah, just set memory, segment offset, and value. So, okay, fine. So set memory, and the value, or the location one, is F61 colon 1 DDA. And we have a 2 there now, so that means we have 2 lives left. So let's say, I don't know, 9. Let's give ourselves a whopping 9 lives. Okay, so memory changed 1 byte, which is, it should obviously be 1 byte, but okay, whatever. So let's try it now. Let's go back to Pac-Mania. I'm going to press Alt-Pause to close the debugger. And let's get ourselves killed. Yep, look what it did. So the game is not programmed to draw 9 lives. The programmer didn't figure that you would actually have that many lives at once, so it only renders up to 4 lives here. But I think the lives are actually in memory, because you can see now I put a 9 in here, and now we have an 8 here. So it did actually decrement it properly to 8, and I'm going to guess that if I die again, I won't lose one of these lives here. Let's try it. So let's get ourselves killed. Yep. And it still shows 4 lives. So, and it did actually decrement that 8 down to a 7 here. So it is counting down the lives. So it did take the number of lives they put in. The game itself just doesn't render them, like it doesn't draw them here in this area, but it does know how many lives you have. So it will actually give you that many lives in the game. So you could put in like FF to give you 255 lives, unless it's a signed integer, in which case that would give you a negative number of lives. We can try it and see, but I don't know. I'll leave that an experiment for you folks if you want to try something like that. But that's kind of how you do it. I mean, that's how I did it. If you folks know a better way, if somebody wants to suggest a better way of doing things, please feel free to sound off in the comments and suggest a better way of doing things. But again, you can see it was fairly easy. We didn't have that many things with a number 3 in memory. And so I found the byte fairly quickly. Now, granted, I knew I was looking for a 3 instead of a 2 because I'd done this before with this game. So, that's, obviously some prior experience with the game helps. But again, this is the best case. This is the simplest case. 7 lives represented by a number 7 here in memory. So that makes it relatively easy. the programmer could have made it much harder for people to do stuff like this, and he could have, put like a 3 somewhere and a 4 somewhere else, and then the game would constantly add 3 and 4 to give you 7, and you would have to like really go through the memory and find the locations that it's referencing to figure out how it gets that number 7. So, there are tricks that people can use to make it harder for you if they really want to, but this is kind of how you do it in the simplest case. So, okay, cool. So this is how you could cheat in Pac-Mania, but how would we turn this into a trainer? Now we come back to the subject of interrupts. And what I'm actually going to do is let me get out of the game. Quit the game here. And what I'm going to do is I will, let me close this as well, because I don't think we need that anymore. I mean, we've seen how to do this, so I don't think we need this data now. I'm going to actually reset the virtual machine. Okay, and I'm going to come back here. Hold on, let me start the debugger. I have to do Alt-Pause to activate the debugger. Now, if we look at memory location 0, 0, because that's where the interrupt vectors are. So if you're working with interrupts, remember the location of where the interrupt jump vectors are stored in memory is easy to remember. It's literally at the very beginning of the computer's memory. So we say data view is just, can I just say 0? Yes, you can. It took us to byte 0. So that's it. So this byte right here, actually these 4 bytes, this is a 4-byte jump vector because these interrupt vectors are all 32 bits, so they're 4 bytes each. So these 4 bytes here are the memory address, that's the memory location for interrupt 0. So that's interrupt 0, the next 4 interrupt 1, the next 4 interrupt 2, and the next 4 interrupt 3. So you have 4 interrupt vectors per line. So this is interrupt vectors 0 through 3. Second line is 4 through 7. And then here, starting at byte 20 hexadecimal with this 84 right here, this is showing you the jump vector for that all-important interrupt 8 that we want to use. Now, what's the problem here? Why might we have a problem doing that? Let me take a screenshot here. I'm going to take a screenshot, and I will open up Paint and show you what we got here. Okay, that should be fine. Resize the window a little bit. Okay, so here we go. So this is a screenshot that I've just taken of this memory area here. So you can see, whoops. Oh, silly Windows. Windows does so many stupid things. Why is Windows so silly? It minimized these windows for some crazy reason because I brought the window up here. I hate when Windows does stuff like that. Okay, but this is a screenshot that I just took of this. So you can see this is where we started. These are the interrupt vector addresses that we started with. So what I'm going to go ahead and do now is I will run Pac-Mania again. Let's just start the game. And let's activate the debugger. And look at what's happened. Our game, Pac-Mania, has actually changed the address for interrupt 8. Because remember we said it was here at byte 20? Pac-Mania has actually made its own vector, because it's code segment 820, so you can here's the 8 and here's the 20, because the bytes are stored backwards. So first you have the offset here, and then here's the segment, and it's also little endian, so you have the 20 here and then the 8 here. But the Pac-Mania has created its own interrupt 8. In fact, not only that, it's created its own interrupt 0. It didn't touch interrupt 1 or 2 or 3 or 4, 5, 6, 7. Okay, so it didn't change all of them, but it actually changed several interrupts here and made its own interrupts. So If we were to write a TSR, that basically what the TSR would do is it would make interrupt 8 or some similar interrupt just constantly write that value to memory. You know, that byte that we found in memory that shows how many lives you have. We would just use the TSR to constantly, like 18 times a second or 18.2 times every second, we would write a high number of lives into that memory byte. And so because we're constantly writing a high number of lives into that memory byte, our lives can never go to zero. We'll never have time to lose all those lives because the lives keep getting replenished multiple times a second. And so that would basically keep us alive forever. But we're going to have a hard time doing that because the game actually took control. It created its own interrupt 8 handler. Probably because, you know, it's a game that uses the keyboard, and so it probably is doing something with the keyboard. It probably took control, you know, of the keyboard from the BIOS, and it's making its own keyboard routines or something like that, which is okay to do in a sense because it's a DOS game. And, you know, back in the DOS days, again, like I said, DOS didn't really have a very good concept of multitasking. It was possible to multitask, but the sort of paradigm in DOS was that you just had one program running at a time. And it was generally okay, like it was not frowned upon for programs just to take up the whole computer, just to like basically grab all the resources in the whole entire computer, just take all the memory, all the interrupts and everything, and just say, okay, I'm grabbing these now for as long as, you know, as long as this program is running. It sounds like bad behavior. I mean, you could argue that it is, but again, in a way it was fair because these games were sort of written with the idea that they were the only thing running on the whole computer. You wouldn't be running this and a bunch of other software at the same time. You just didn't really, you know, you could, but people didn't generally do that in DOS. In DOS, the idea was that you have one program running at a time, and so it was okay for programs to do stuff like this. This is also why strong memory protection didn't exist because the trainer that we're going to write is essentially one program writing into another program's memory. Our trainer is going to be one program, and it's going to literally be writing into the memory of the game, which is prohibited by most operating systems today. I mean, stuff like Windows and Linux and, you know, any other major operating system today will prevent a program from doing that. It will prevent one program from writing into another program's memory. That's a memory access violation. But back in the DOS days, that was not unusual. And it could be done because there wasn't the kind of memory protection that we had today. So we're going to do that, but we're not going to do that with Pac-Mania because Pac-Mania takes control of the interrupts that we could use for those purposes. And I'm not saying it's impossible, but I got to be honest, I don't know how you would do it for a game like this. And a lot of games do something similar. A lot of games do sort of seize these interrupts and make their own interrupt routines. So I don't know exactly how you would do something like that for games like this. If anybody knows, please let me know in the comments. I mean, I fully admit that I'm pretty ignorant about this stuff. Like what I'm saying in this video is just like the very most basic stuff. This is really like the absolute most basic stuff about writing a trainer. And even stuff like this, I had to spend a long time sort of piecing together myself because I'm not, I never learned this stuff. I had to teach myself. And everything that I'm saying here is pretty much self-taught because I just had to gather this information myself. So anyway, yeah, so Pac-Mania is a great game. I mean, I like this game. I agree with the statement that it's quality software. I think it is a well-made game. But I'm not going to make a trainer for this because whatever attempts we would make to preempt the interrupt, that code would itself be preempted by the game when it runs. So I'm not gonna do anything further with this game. Although, in all fairness, one other thing I just want to show you, just to kind of give you an idea. I don't know if this is enlightening at all, but let me go into Windows 3.0, which came out in, I believe, 1990, if I'm not mistaken. And what I'm going to do, so by default, Windows 3.0 tries to run in, if it can run in this mode, it tries to run in what it calls 386 enhanced mode, which is basically virtualization. This is basically the virtualization that was made possible by the 386 processor. This wouldn't have been possible with the 286. The 286 just didn't really have this kind of virtualization. But the 386 introduced a sort of virtualization. In essence, what Windows 3.0 does in this mode is, if we go here to the main program group and run a DOS prompt, what it's actually done is it's created a virtual machine just for our DOS prompt. So the Windows GUI is still running in the background. It's still there. In fact, if I do a memc command here, you can see that Win and Win386 are still running. but Windows has essentially made a virtual machine just for our DOS session here. And I think I can press Alt-Enter. Yeah, and it actually runs in a window like this. You can actually run a DOS prompt in a window. Now, you can't do graphics in a window. If you want to run a graphical program like Pac-Mania, we'll have to go full screen. But I can start running Pac-Mania here in Windows, and it will actually work. And if I do something like Alt-Enter, now that freezes the game. The game can't run in real time when it's in a window, but basically at least Windows does let you turn it into a window briefly so that you can kind of, I mean, I don't know if this is very useful because it doesn't run when it's in a window like this, but you can press Alt-Enter and see that Windows is still running in the background. This DOS session is actually running in a window, and it's virtualized. Windows has used the 386's virtualization capability to essentially make a VM. This is a VM. I mean, it's not quite a VM as we would think of VMs today. You know, not like something you'd make in VMware or VirtualBox or something like that. It's not quite that sophisticated, but this is, for most intents and purposes, this is a VM. It's a virtual machine with its own memory space and its own interrupts that's running separately from the machine that's running Windows still in the background there. Oh, I'm wrong. It can actually run in a window. Check this out. I am running a DOS game in a window in Windows 3.0. I am running a DOS virtual machine in a live window in Windows 3.0. That's pretty awesome. And if you force Windows to run in real mode, so I'm going to quit out of Windows for a second. If you're in Windows with the /R parameter, there's also /S for standard mode. I'm going to do /R for real mode. And this is actual real mode. This is now running Windows in real mode. So yeah, real mode, and it can only do the first megabyte of memory because there's no such thing as memory. Like before, I think it said we had something like almost 80 megs of memory. Now we only have the initial like 1 meg of memory that DOS can access in real mode. So nothing super fancy here, but still, even now, sorry, wrong program group. I didn't want to go to games. I wanted to go to main. Even now, we can run a DOS box. Now, we can't windowize it anymore. We can't. This is not virtualized because we're not running Windows in 386 virtual mode. We're running in real mode here. So essentially what we've done now is we've interrupted Windows. Windows is no longer active. Windows is still there. I mean, its memory is still there. It still exists as a process, but it is not running. It has basically given over full control to our DOS prompt here. And we can still run Pac-Mania. We can still run the game and still do all the stuff that we did before. But we can't switch to Windows while this is happening. Basically, because this is real mode, there's only one process that can run at a time. So this is the only thing running on the computer right now. Windows is not running in the background. But, still, Windows is basically able to kick over to a DOS prompt, and you can run games like Pac-Mania that take over the interrupts and stuff like that. And when you're done, you can exit out of that, and we're back in Windows. And all of this with real mode, with less than, with like the standard 640K of memory. That is pretty impressive, I have to say. I mean, that Windows is actually doing all this juggling, that it's actually keeping all these balls in the air and managing the resources of all these processes seamlessly is pretty darn impressive, I would say. I mean, this is Windows 3.0 from 1990. I feel like that's pretty impressive. And a lot of people will say, well, but the Amiga did it better. The Amiga had better multitasking, or Mac OS had better multitasking, or OS2 did it better, or whatever. I mean, yeah, okay, maybe, I'm not saying Windows was the best, but still, this is pretty good. I mean, this was the time when Microsoft made pretty good software. I mean, I know it's hard to imagine when we look at Microsoft today, but there was a time when Microsoft actually made fairly decent software, and Windows 3.0 was not too bad for what it was. It didn't have multimedia capability that came with Windows 3.1, but that you can do this kind of stuff with Windows 3.0, I think is pretty impressive, especially with DOS games like that, which like try to take control of the whole computer. They like take control of all the interrupts, and that Windows can virtualize that effectively and make a VM for a, I think it's pretty impressive. I think that is pretty darned impressive. So kudos to Windows 3.0 for doing stuff like that. But anyway, sorry, that was just a little aside. That wasn't really what I wanted to talk about. So what we do want to talk about now is making a trainer. And I'm going to leave Pac-Mania behind now because it's going to be too difficult for me. I'm going to switch to a different game. And this is a game which I have featured on my channel before. It's not a very good game. So you might ask, why this game? Well, because I couldn't find another game where I could actually find the correct byte locations to, that I needed to modify in memory, where I could actually find the byte locations that would let me cheat, and a game which didn't take over the interrupts the way that Pac-Mania does. So the game is FBI Fred, and actually, you know what I'm going to do? I'm going to just going to start with a clean slate. I'm going to reset the virtual machine again, and let's go into FBI Fred here, and I'm going to start the game. Type your three-letter initials. Lat Blight. Yes. Okay, and this is FBI Fred. So let's play the game, and I am going to, let's see, okay, the game's running, very good. We'll start the debugger again, and we can take a look at the memory jumps, the interrupt vectors, compare them with the default state. So you can see FBI Fred does not change the vector for interrupt 0. For interrupt 8. It did change it for interrupt 0. I'm kind of wondering why it did that. Why does it change the interrupt for the vector for interrupt 0? It doesn't seem to have changed any of the other ones here. All the other ones here, at least the first several. Oh, it looked like it changed interrupt 9. That's interesting. It changed the vectors for interrupts 0 and 9, but not 8. That's interesting. I wonder why it did that. What are interrupts 0 and 9? Okay, let me quit the game for a second. Let me get back to Help PC. I'm just curious, what does Help PC say? Interrupt 0, isn't that the divide by 0 interrupt? Hold on, what's interrupt 9? Keyboard. Okay, so FBI Fred is using its own keyboard handler. Okay, that makes sense actually, because keyboard handling in DOS is bad for games because of the repeat thing. I think I made a video about this not too long ago, talking about keyboard routines in DOS and how the default DOS keyboard handling is very bad for games because it relies on like there's an initial pause and then a repeat rate. So actually, it's good to make a keyboard handler for a game like that. But interrupt 0, I think it's divide by 0. Oh, wait, no. Oh, no. Oh. These are CPU exceptions. That's something different. Is it? Wait, no. No, it is divide by 0. Okay. That's odd. Why is it grabbing the divide by 0 interrupt code? Okay, no idea. I have no idea why it's doing that. Don't ask me. Ask the guy who made the game. I think his name is Rafael Salgado. If you can find him, ask him why he's changing the divide by 0 code. But for our purposes, we want to use interrupt 8, and FBI Fred does not play with the vector for interrupt 8. That means we can use it. Great, good news. So once again, we need to find the location that we want to change. So I'm going to cut this one short because we've already seen how to do it. So I'll just say, I think I wrote it down somewhere. I must have written it down somewhere. So let me Let me just get back into the game for a second, and I'll just explain how it works in this game. So you can see your health is these yellow hexagons down here, and we have eight health points. But the way that this game does things, again, this is just something I had to find out by poking through the memory code. You don't start off with 8 hit points. Instead, the relevant value here starts off at 0. And actually, this might become more apparent if we actually play the game. Let me start the game and let's watch what happens. So right now I'm at full health, but watch what it does when we get hit. I'm going to wait for us to get hit by something. There we go. See what it's doing? It's actually, I don't know if it's apparent, but what it's really doing is it's filling in those hexagons with black. So right now, instead of having 5 health points, or 4 now, it's actually adding damage points. So it's counting up, not down. So we're looking for a value that goes up each time. So right now we need a value that has 5 because we've taken 5 hits. So it starts off being 0, then it goes to 1, 2, 3, 4, 5. So right now it would be 5. So I'm just going to go ahead and say where it is, because I found it before, and I'm not going to go through the process of finding it again. Where is it? It is... I believe its location data segment. So we'll need to look up the data segment. And then after that, it's offset C9B2. That stores how many damage hits you've taken, how many damage points you've taken. It starts at 0 and then it counts up from there. So let's try working with that. So I'm going to go ahead and run the game again. And let me start the debugger here. And I am going to look for data location. What did I say it was? DS. We want the data segment. So the game is using data segment of 17B9. That's fine, 17B9. And the offset, I think I said it was C9B2. So it is 0. That fits, but you can see there are a lot of bytes that are 0. So I'm going to hope that I did the right thing. So I'm going to say again SM to set memory. So we'll say, as a test, we'll say set memory, and the address here is 17B9 colon C9B2. And I'll put in a value of 5, just as a test. So theoretically now we've taken 5 points of damage. How's that? Does that actually get reflected in the game now? It looks the same, but wait until we get a hit. Wait until we get hit, and I think we'll see something interesting happen. Yeah, see what it's done? So the game doesn't expect you to suddenly jump from 0 points of damage to 5, which is why it didn't. It basically just draws the next hexagon. It fills in the next hexagon with black after you get hit. So that's why it looks kind of weird. You're not supposed to have a hexagon here that's black and these still yellow. It's supposed to count up from the left because I just jumped to 5 points of damage. That's why it did this. But we found the right location. So I mean, we're going to see some graphical glitches in this game because it's not built. The game was not developed to have people just arbitrarily start punching values into memory, so it's going to look a little bit weird in a couple of cases, but we definitely have the right byte. That is definitely telling the game how much damage we've taken. So, okay, cool, that's fine. So let's quit. We know the location we want. And it's time to write our trainer now, because we have a memory location. It's time to finally write a trainer. It's taken long enough. I've only been talking for an hour. So I am going to go to A86, which is my assembler of choice when I'm writing assembly language programs, and I'll create a program called FBI train.asm. This will be our trainer for FBI Fred. So, so where do we start? I'm just going to copy from my notes. So again, and all this should be in my previous video making a TSR, so I'm going to speed through a lot of this. A lot of this might seem very opaque or obscure if you haven't seen my video making a TSR, but since that's something I've already covered, I'm not going to go into it in depth now. I'm just going to breeze through the TSR stuff. So step 1 is get the interrupt vector of interrupt 8, because we want to change that. So first thing to do is turn off hardware interrupts by issuing a CLI command, clear the interrupt flag. Now we do move AL8, specifies interrupt 8, and move H35. This is the command to get an interrupt vector. And now we run int21h, which is a service of DOS, which tells you the interrupt vector. So, where is the vector now? I don't remember. Anyway, okay, let's see. So, step 2, make interrupt C8 behave like interrupt 8. So, interrupt C8 is not used anyway. It's the typical sort of user interrupt, so we can go ahead and make use of it. So what I'm going to do here is we need the offset in DX. So it's in BX. So interrupt 21 returns it into BX, but we need to get into DX. So we can just say move DX, BX. That should be fine. And then we need to get so it put the segment that we need in ES. We need to get that into DS. You can't just say move DS ES. The Intel x86 assembly language doesn't have, or machine language doesn't have this instruction. So you have to do it in a roundabout way. You have to push ES onto the stack and then pop it off the stack into DS, which is equivalent to move ES into DS, except this command doesn't exist. So you have to do it using these two commands. Okay, that's fine. So, the above commands set DSDX to the vector that we need, I believe. Okay, that's fine. So, to the vector of interrupt 8. Okay, fine. Now we want to set interrupt C8. So I'll say move C8 into AL. And because we're using A86, it has this quirk where you have to, if your location starts with a letter, you have to precede the letter with a 0 so that it knows that it's a number, it's a hex number, because otherwise it will think that that's a label of some kind, like a labeled memory location or variable name. I'll put H here just for consistency's sake, just to, even though it's clear. I mean, if there's a C, obviously it has to be a hexadecimal number, but still. Okay, then in AH we'll put 25H, which is the command to set vector make interrupt C8 behave like interrupt 8. And now interrupt 21H. Cool. So we have now set the vector of C8 to the same as vector 8. This means that vector C8 will do the exact same thing as vector 8. Why is that useful? Because now we're going to grab vector 8 for our own nefarious purposes. So, step 3. Set interrupt 8's vector to your own. Function. Okay, so so what do I want to do? I want to, so DX will contain the offset of our TSR interrupt. We don't have this label yet, but we'll make it later. We'll need to remember it's called TSR int, that's fine. And again, DS needs to point to, so DS needs to point to this code here, the code that we're running here. And again, there's no command like move DS CS, so again, we have to do this indirectly. We push CS, push the code segment, which is where our code is running here. Let's say this routine segment. So DS is now pointing to the segment where this code is. Okay, And what do we want to do? Well, now we are going to set another vector, except this time we're setting vector 8. So move AL8, move H25. So this sets interrupt 8 to behave like our new interrupt function. And then I'll call interrupt 21H to do that. OK. And step 4 is do interrupt 2131, and you're done. Interrupt 2131 is the routine to make a TSR. It makes a call. It creates a terminate and stay resident program. So AL needs to contain the exit code for batch file. I'll just put in 0 because 0 means no error. It's not really that important, but it's nice to do just for niceness sake. And DX needs to contain how many bytes we want to reserve for this TSR. I'll just say FF. 255 bytes should be more than enough. Yeah, I mean I'm pretty sure TSR is smaller than 255 bytes, but that's fine. And then H31 is the command to make this into a TSR. And then we call interrupt 21H. Boom, done. That's it. We have a TSR. We're now resident in memory. This program will end, and it will remain resident in memory even after this segment finishes running. And what we want to do now, we made a we call on a label called TSR int, TSR interrupt. It's time to define TSR interrupt. This is the actual code that we want to do. So what are we doing here? First we want CLI to disable interrupts again. It's good form to, actually we don't even really need to, I usually do push A to save all the CPU registers, but actually I don't think we even, now let's do a push A just to be safe, because I'm going to do a comparison later, so I want to, that might, yeah, so push A stores AX, CX, DX, BX, SP, BP, SI, and DI. It does not save any of the segment registers, so if you are going to change a segment register, remember that you have to push that onto the stack and pop it back later. But that's okay, we're not doing that this time, I don't think, so we're okay. We should be okay. We should be okay. Save all the CPU registers for later. Okay. Your interrupt code goes here. Whee! Okay. What are we doing? So normally I would do a push DS because we're going to be using the data segment, but actually we are going to use the game's data segment, because the game will actually set its own data segment, and I know the data segment offset to use, so actually we don't even need to change the data segment, so we don't need to push it because we're not going to change it. We're not going to change the data segment, so I'll just leave it as it is. We don't need to do anything with it. All we need to do actually is say, what was the location? I think the location was C9B2 hexadecimal, is that right? I think that's right. I think that's where I said the, I hope that's right. Okay, so what we want to do then is we want to say, move to that memory byte. So how do we do this? I'll put this in, oh no. Oh no, Larry Cole. I'm using a German keyboard, and my German keyboard is not letting me type the square brackets that I need here. I think I had this problem. I think I had the same problem last time when I was doing something like this. Okay. Rather than fiddle around with how to do this for however long in DOSBox, I am going to open the file outside of DOSBox. Give me just a moment. I'm just going to come in here in Windows, and in Windows I am going to find that file. What do you call it? FBI train.asm. Here it is. So I want to be here. So I'll put a opening square bracket there, closing square bracket there. Save, close. Okay, fine. And I'll continue the rest in here. I guess I could do it just as well in Notepad, but what the heck. Okay, so so we want to move something to this memory location, and the value we want to move there is 0. We want to take 0 amount of damage. So what this is going to do is 18.2 times every second, this is going to take the number 0 and put it into that memory byte, which tells the game how much damage we've taken. So it's going to constantly tell the game, 18.2 times a second, that we've taken no damage. And I do need, I believe, do I need to, I think I do, I need to precede this here with a B for byte. This tells the game that it's a byte, so it's 1 byte as opposed to a, for example, a W. You could have a W here for word. A word in this context is 2 bytes, 16 bits. We do not want to do that. We are working with 1 byte here, so I'll say B to say, no, that's 1 byte. And yeah, it's at memory location, CNN. Oh, and again, don't forget to put a 0 here, because if you start with a letter, if your hex address value starts with a letter like A, B, C, D, or D, E, or F, then 86 will think it's a label. So proceed it with a 0 so it knows that's a hexadecimal number. Okay, that's it. This is all we're doing. We're just telling the game, move 0 into that location. I think that's it. That's all of this is just for that one line. That one line is the key here. All we really want to do is that one line. Okay, let's finish off here. Let's do the sensible thing and finish off nicely here. So first we do pop A to restore old register status. I mean, it looks like we didn't change any registers, but still, it's good. Just it's good practice to do this. And then, so we're done now. This is our routine that's done, but don't forget to do interrupt C8 as well. Do the old interrupt 8 as well. This, remember, C8 is now interrupt 8. So whatever interrupt 8 does, we don't want to stop that from happening. We want to keep doing that. That's why we pointed C8 to it. So we're going to call C8 now to do whatever the old interrupt 8 code did as well. Because we are now interrupt 8. We are interrupt 8 here. So we want to make sure that we nicely do what interrupt 8 is supposed to do. We've done this. We've done this. This is what we came for. But we want to make sure that we do whatever interrupt 8 was actually supposed to originally do. So okay. And at the end, there's just some stock code. So you do a push AX AL20H, and you do an out 20H AL. This sends an end of interrupt signal to the 8259 interrupt controller. Just something you need to do as a matter of course, and then restore the old AX so it doesn't get garbled. This re-enables interrupts. This is the opposite of CLI. And then IRET is an interrupt return, signifies, or signals, might be a better word, signals that the interrupt is over. That's it. We're done. Save and exit. And I'm going to try to assemble this, FBI train.asm. We got no errors. That's a great sign. We get 0 errors. So, I'm just thinking now, just to make sure that our, let me go back to the debugger just for a second. We are changing memory address. So So the data segment right now is 749. So if I say 749, what was the address that we were going for? It was C9B2, wasn't it? Yeah, so right now it's... I wonder if this is bad. Let me reboot. Hold on. Let me reboot the virtual machine and just see what's going on here. I just want to make sure that we're not doing something super crazy here. I mean, that's interesting. It's still E9. Normally when you do something like this, normally when you are testing trainers and stuff like this, if you've got no game running, the code that you're shooting at is probably going to have zeros in it. Usually the memory of the computer is just filled with a bunch of zeros if there's no program running there because there's no data. But something here is actually putting data there. There is data there. That's not great because it means that if I run this now, it is going to overwrite that data with that 0. But oh well. I mean, it's just a virtual machine running DOS, so worst case scenario, DOSBox crashes, but it probably won't. It's probably not that critical. All right, let's try this. So I'm going to go into 86. I'm going to run FBI train. Okay, our VM hasn't crashed. It's still responding to input. That's good. That's a good sign. It hasn't crashed yet. And if I come back to the debugger, look what it's done. It has actually set that byte to 0. It did, in fact, set the byte to 0. And if I change it now, if I say set memory 749, C9B2, if I change it to something like, I don't know, 55. I've changed it to 55 now. If I kick out of the debugger and go back in, yep, our TSR is working. It is actually forcing that byte to 0. Every second, 18.2 times per second, it is resetting this value to 0. So if we get hit in the game, we'll have like 1 point of damage for a fraction of a second, and then it'll get knocked back down to 0. So it is working. You know what I'm going to do? Well, let's run the game first. Let's just run the game and see how it looks. Let's just make sure that it looks correct in the game. Play the game. All right, mice. Hit me. Or maybe they're rats. I don't know. Rats and birds. Come at me. Come at me, bro. There we go. That's our first point of damage, but subsequent points of damage do not hurt us. Yeah, see? I keep getting hit, but it stays at 1 point of damage. So we do take a point of damage because this isn't really preventing us from taking initial damage. It's just changing it. After we take a point of damage, it keeps resetting that back to 0. So we do get the first hexagon filled in black because we did take 1 point of damage, but that 1 point of damage keeps getting reverted. And the game is not checking that. The game is not checking to see how much damage we have because normally your damage doesn't just disappear. Your damage keeps going up and up. The game is not made to just have the damage go up and down. So it's not checking to see what our damage is. If it did, it would actually fill in this hexagon again, but the game just wasn't programmed that way. So that's fine. But the game is working now. We can get hurt as much as we want. We can take a bunch of hits. We can run into as many damaging things as we want. And we will not sustain damage beyond that first hit because that one hit that we took keeps getting reset to 0 in the game's memory. So I can run into these robots and keep getting hurt by the robots. They will not hurt me beyond that 1 point of damage that I already took. So we can pick up that GF thing, whatever that is. I don't know what that is. I can pick up this carrot. I can pick up this key. Pick up this fish here. And yeah, I can just have a jolly old time getting hit by these robots forever, and I'm not going to die. I think I said last time I played this game, I'm actually quite fond of this game because of how it looks. I really love the EGA. I really love the colorful EGA graphics of this game. It controls very badly. The controls of this game are terrible, but it is a nice looking game. It's actually a nice experience to be in this game. I actually quite enjoy this game. It is a nice experience to play this game, even though it looks quite bad. I wonder what's happened here. So, that's interesting. It looks like I took a second point of damage, and for some reason the first hexagon here is now flashing. So, we're making the game do something that it's not designed to do. So, you're going to have stuff like this. You're going to have weird glitches like this because the game is not really designed for whatever we're doing with it. So, okay, we're almost done. We've made a trainer for this game. This is essentially a trainer for FBI Fred, and it's working, as you can see. But let me go back to the debugger and do a couple of things to finish off here. Just a couple of kind of finishing touches. So one thing that is a good idea to do is to put a check into your trainer to make sure that the game is running. Because what you really don't want to do is start corrupting memory of some program when the game is not running. Now, of course, you shouldn't keep this trainer running at all times. Like, you shouldn't constantly have the trainer running if you're doing something important, like if you're editing documents or, whatever stuff you normally do with your computer. Don't keep trainers like this running in the background because they will interfere with memory and they could do some weird stuff. So only run this trainer when you're actually playing the game that it's designed for. And when you're done playing the game, reboot the computer so that the TSR goes out of memory. Actually, a really good trainer can unload itself. It is possible to make a trainer that unloads itself, that terminates itself as a TSR, if you want to. We're not going to do that today. That's a little more advanced. Maybe that's for next time. But what I do want to do is put in a basic sanity check here so that it doesn't, because what it's doing now is it keeps writing, as you saw, it keeps writing that value to memory even when the game's not running. What I would like to do is have it only do that when the game is running. So let's take a look through the game's code. I think I saw a string somewhere here. Let's look for like an identifiable string in the game that is clearly from the game. I think if we go farther up, if we go farther back in the game's data, there were at least a couple of them. PQRSTUVW, that might be one, but let's look for something a little bit more distinctive. I remember there was one that, let's see, I think I'll recognize it when I see it. I just need to see it. How far back did it go? Golly gosh. Yeah, it's a fair way. I mean, the game has more data than you might think. I mean, all this data, I think all this data belongs to the game. So yeah, there we go. So there's this, for example, version 1.5 EGA, VGA, Pro Graphics. Pretty sure this is from the game. Pretty sure this is from the game. But there was a string about typing in your name or typing in your 3 initials. Because remember at the beginning it says type in your 3 initials. I'm looking for that. Where was it? It was somewhere. Come on, get me this far away. Where did I think I wrote down, hold on. Yeah, I think I did write down where I put it. Isn't it? Oh yeah, I think I went way too far. Isn't it under, it's not that far from where we put the, it's not that far from where we put the damage value, like the 0 for 0 damage points. It's something like, I wrote C6B2, is that right? That is not right. Oh, wait. Oh, wait, I'm totally in the wrong place here. The data segment here is 18FF. I need to be looking, herpaderp, I need to be looking at 18FF, not whatever we're doing here. Okay, so data view, change data view to 18FF, because that's the game's data segment that it's using now. And we were looking at location C9B2, right? Yeah, so that's how much damage we've taken. But if we go back in the memory a little bit, there was Here we go. This is what I was looking for. Type your 3-letter initials, and I don't know, it just says hi there instead of, I think it's supposed to say hit enter or something. It just says hi. Okay, whatever. But yeah, it is C6B2. Okay, so the location of this is C6B2. In fact, I'm going to open up Notepad for a second and let's make a note of that. So we're looking for data segment C6B2, and it's the letters capital T and lowercase y, which is, as you can see here, it's the hex bytes 54 and 79. Okay, so let's do a check for that. So I'm going to actually quit out of the game. Oh, it's by Richard Spitzano. So thank you to Richard Spitzano for making this game. I know I keep ragging on this game and saying about how terribly the game controls. It does control very badly, but it's still a great looking game. I still enjoy this game just because it looks pretty cool. Hey, I got 750 points. That's not bad. Okay. All right. So what did I want to do? I wanted to come back here and edit our trainer to put in a nice check. Oh dear. Error CPU illegal unhandled interrupt called 6. Okay, I think our, I'm going to reset the virtual machine. I think our trainer did something crazy to the editor. It prevented the editor from running correctly. So see what I mean? If you don't want your editors or your trainers to interfere with stuff, then don't leave them running when you're doing other stuff. Although, what I'm about to do will help prevent stuff like that from happening, because I'm going to put in a, whoops, I reassembled it. I didn't mean to do that. I meant to edit it. There we go. So this is the line that actually makes the change. But before we do this, you know what I'm going to do? I'm going to add a check before this. And the check that I want to do is, what was it? Right. So we want to look for these values here. So what I'm going to do then is I'm going to say compare, and now we can use W for word. Now we can say W for word instead of B for byte, because we're comparing 2 bytes. And I still can't type square brackets here, so let me just actually copy this. I'll say copy and paste. Okay, so the location we're looking at is C6B2. Yeah. Okay. C6B2. That's interesting. We have C6B2 and C9B2 there, exactly 300 hexadecimal bytes apart. That's interesting. I wonder if that's a coincidence or if that's somehow intentional. I don't know. Okay, so we're looking at C6B2, and we want to look for hex value 7954. But again, they're backwards. They're little endians, so we actually want to do. Oh, this is actually what I need to type. Sorry, I meant to do this. I meant to do 5479 because in memory it looks like 5479, but they're actually backwards. So we actually need to type 7954 hexadecimal. So that's TY backwards. Some people might not like my use of the term backwards to mean little endian. I recently got a comment on an older video where somebody said it was really funny that I'm saying backwards to mean little endian. That's just how I call it backwards. If you think that's silly, yeah, you can say it's little endian. I mean, yeah, it is little endian, but it's backwards. It's counterintuitive. Okay, and so what we need to do now is we need to say jump if not equal. So if that memory address does not equal that T and that Y, that means FBI Fred is not running, and we shouldn't do this. So I'm going to make a label called don't do it. So if this memory location does not equal this value, then jump if not equal to don't do it. And I'll put the label down here, don't do it. So this is now saying, this is skipping over the actual change. So if FBI Fred is not running, if we don't find this value in memory, then don't do it. It's a trap. Skip over this line because otherwise this will start screwing with memory of some program that's that's not FBI Fred. So yeah. And while we're at it here, while we're here, I'm going to go ahead and toss in a couple of improvements because there's also the ammunition in the game. There's also there are laser shots and bullets. So I'm just going to go ahead and toss those in now. So the number of laser shots that you have is at C906. And you start off with 5, so I'll just say 5. You can actually even put 1 here, and you'll always have 1 left, which means you'll have infinitely many shots because there'll always be 1 left. But what the heck, I'll just say start with a starting value of 5. And so that's the laser shots, and then there's also bullets, which is, I think, at C908. And again, I just found these, again, just by poking through the memory, just looking for things that looked likely. Took a while to find these, but not super long. Again, less than an hour of looking. So there we go. So now we should have, so what we've added here is we have unlimited ammo for laser shots, unlimited ammo for bullets because 18 times a second the game will write these values into memory. And we also added a basic sanity check, which basically says that if this is not in memory, then don't do it. Don't actually write these into memory because the game is not running. So this will prevent those writes from happening until the game has actually started. So I'll say save, quit, assemble that, and run it. Oops, I put a... It's running though, isn't it? Yeah, you can see our TSR is running there. You can actually see the TSR is there running. So we can check 2 things now. Let's check that it actually still works in game, that our check is working. Come on, come at me, bro. Okay, that's our first hit, that's fine, but yep, but the second hits are not registering. So it is correctly doing that. So it is correctly recognizing. If it wasn't recognizing that byte pattern, those 2 bytes, that uppercase T and the lowercase y, then it wouldn't actually be writing those values, but it is. So that means that it is correctly recognizing the game signature. If you want to be really paranoid, you could check like for a longer string. You could check for this whole string, type your 3-letter initials and hi. You could check for the whole string because that's probably not something that you're going to find anywhere else except in this game, but this is probably good enough. Again, I mean, you shouldn't leave the TSR running in the background when you're doing other stuff with your computer anyway. You should only run the TSR when you're running this game, and then when you're done with the game, then reboot the computer to get the TSR out of memory. Okay, so that's it. The last thing I think is then just to check those things about the ammo, because I also added the possibility for infinite lasers and bullets. So I'm going to shoot a laser, and the game, you can see on the left-hand side, it actually counted down, it shows that I have 4 laser shots instead of 5 now, and it keeps going down, but see, I can keep shooting the laser even after I run out of shots. So the game is actually... It's not checking how many laser shots you have left. It assumes that if you shoot the laser once, then your laser count goes down by 1. And so that's why it's showing no laser shots here. But it's actually, the value that reflects how many laser shots we have is actually independent from the value that dictates what's shown here. And actually, if I keep shooting, see what's happening there? It's actually drawing these blue lines here. So it's actually creating graphical artifacts because it added these blue lines here to cover up those yellow laser shots that I had, and then it keeps going down like that. As I keep shooting, it keeps going down because that's what the code does. The code basically just draws these blue horizontal bars to cover up your shots when you shoot the laser. And it didn't expect me to still have shots after those initial 5 were spent, which is why now it just keeps going down through the memory. It keeps going down through the video memory, just adding more and more of these blue bars. The same as with the bullets. If I shoot a bullet now, so I'm technically out of bullets, but I can keep shooting. And it's going to eventually, I think, do something similar. We're going to start seeing some more graphical glitches like that happen. Yeah, see that on the right-hand side there? Now it's happening over here. It's drawing more blue bars to cover up those shots that I have, and it doesn't realize that it's doing that in the wrong place. Because again, the game wasn't designed to still have bullets after the initial 5 bullets, so it is now doing something really crazy with the graphics. There's probably a way to fix that. I didn't find how to fix that in the code. I'm sure it's possible. If you're interested, you can, I'll leave that as an exercise to you viewers to find yourself how to do it. But yeah, that is how to make a trainer. We've made a trainer for FBI Fred that gives us infinite ammo and infinite health. That's it. Let's go ahead and quit. And yeah, like I said, I mean, our trainer is still running there. If we really wanted to be cool, we could have the option of uninstalling the trainer when we're done. But like I said, I'm not going to do that this time. This video is already, wow, I've been talking for over an hour and a half. So this is already more than enough for a first time. So yeah, that's that. And like I said, again, once you're done with the game, you should restart anyway. Reboot your computer. Don't leave the TSR running in memory because it is going to do funny things with memory. You never know what it's going to do. Don't leave it sitting there if you're not actively playing the game. Restart and get it out of memory when you start doing something else with your computer. So I think that's it. Ladies and gentlemen, this has been a first primer, if you will, on writing trainers for DOS games. I hope that it was interesting. Hope you've enjoyed. Thank you very much for watching. And like I said, I'm open to feedback. If anybody knows a better way of doing these things, if anybody has any advice, if there's anything I missed or anything that I could have done better, please let me know in the comments. I'm definitely open for feedback. I'm aware this is probably not the most efficient way of doing things. This is just the way that I know how to do things, but there's a lot that I don't know. So if anybody knows anything better, then please let the world know. The comments are open. All right. This has been making a trainer for a DOS game. We've made a trainer for FBI Fred. I hope that was enjoyable. Thanks again for watching, everyone, and I will talk to you all later. But until then, I will say goodbye for now.